Hello, myself C.Kalshetti, Assistant Professor, Department of Electronics Engineering, Walchand Institute of Technology, Solpaur. Today, I am going to discuss the three-phase bridge inverter with 120-degree conduction mode. Learning outcome. At the end of this session, students can analyze the three-phase bridge inverter with 120-degree conduction mode. This is the circuit diagram for the three-phase bridge inverter. Now, in this mode, each thyristor conducts for 120 degree and thyristors are fired at the regular interval of the 60 degree. The firing sequence of thyristor is T1, T2, T3 up to T6. If T1 is fired at 0 degree, it conducts for 120 degree and then turned off. During the conduction of T1, T2 is fired at 60 degree and T3 is fired at 120 degree and T4 is fired at 180 degree. This angular interval of 60 degree exists between the turning off of one device and the turning on of other complementary device in the same arm. During this 60 degree interval, commutation is ensured and possibility of short circuit of the source due to the conduction of both device in the same arm eliminated. The conduction sequence of thyristor is 6-1, 1-2, 2-3, 3-4, 4-5 and 5-6. There are 6 operating modes in one complete cycle and the sequence is 6-1, 1-2, 2-3 like this. The conducting thyristor in the different steps are as follows. Now, at omega t is equal to 0 to 60 degree, thyristor T6, T1 are in conducting state, so it acts as a mode 1. From 60 to 120, thyristor T1, T2 conducts. From 120 to 180, T2, T3 conducts. In this way, at the interval of 60 degree, 2 thyristor conducts at any instant of the time. Analysis of three-phase bridge inverter with 120 degree conduction mode. Now, during mode 1, the range of omega t greater than 0, less than or equal to 60 degree, T6, T1 are in conducting state. So, this is the circuit diagram and this is the equivalent circuit. When the T6, T1 are in conducting state, the phase A is connected to the positive terminal of the battery and the phase B is connected to the negative terminal of the battery. Therefore, VAN is equal to plus ES by 2 and VBN is equal to minus ES by 2. And here the third phase is not connected, that's why VCN is equal to 0. Now, determine the line voltage. VAB is equal to VAN minus VBN ES, VBC is equal to VBN minus VCN minus ES by 2 and VCA is equal to VCN minus VAN minus ES by 2. During mode 2, the range of omega t greater than or equal to 60 degree and less than or equal to 120 degree. In this mode, T1, T2 are in conducting state. When the T1, T2 are in conducting state, phase A is connected to the positive terminal of the battery and the phase C is connected to the negative terminal of the battery. Now, therefore here VAN is equal to plus ES by 2 and VCN is equal to minus ES by 2 and VBN is equal to 0. And the line to line voltage VAB is equal to ES by 2, VBC, VBN minus VCN plus ES by 2 and VCA, VCN minus VAN minus ES. During mode 3, the range of omega t greater than or equal to 120 degree and less than or equal to 180 degree. In this mode, T2, T3 are in conducting state, and this is the equivalent circuit. Here, phase B is connected to the positive terminal of the battery and the phase C is connected to the negative terminal of the battery. Therefore, VBN is equal to plus ES by 2, VCN minus ES by 2, and VAN 0. And VAB is equal to minus ES by 2, VBC, VBN minus VCN plus ES, VCA, VCN minus VN minus ES by 2. During mode 4, the omega t greater than or equal to 180 degree and less than or equal to 240 degree. In this mode, T3, T4 are in conducting state. So here VBN is equal to plus ES by 2, VAN minus ES by 2, VCN 0, and VAB is equal to minus ES, VBC plus ES by 2, VCA ES by 2. During mode 5, the range of omega t greater than or equal to 4 pi by 3 and the less than or equal to 5 pi by 3. In this mode, T4, T5 are in conducting state. So effect of this, phase C is connected to the positive terminal of the battery and the phase A is connected to the negative terminal of the battery. So VCN is equal to plus ES by 2, VAN minus ES by 2, and the VBN 0. So VAB is equal to VAN minus VBN minus ES by 2, VBC, VBN minus VCN minus ES by 2, VCA, VCN minus VAN plus ES. Now, mode 6. In this mode, the range of omega t greater than or equal to 300 and less than or equal to 360 degree. In this mode, T5, T6 are in conducting state. So, phase C is connected to the positive terminal of the battery and phase B is connected to the negative terminal of the battery. Therefore, here VAN is equal to 0, VBN minus ES by 2, VCN plus ES by 2. So, VAB is equal to plus ES by 2, VBC minus ES, VCA plus ES by 2. So, these are the waveform. Now, here these are the phase voltage waveform. In the mode 1, the value of VAN plus VS by 2, VBN minus VS by 2. Here, consider these values. In the mode 1, VAN plus ES by 2, VBN minus ES by 2, and the VCN 0. Okay, here VCN is equal to 0. Similarly, consider the phase voltage values from mode 2, mode 3, mode 4, mode 5, mode 6, and according to that draw the phase voltage waveform. Now, these are the line voltage waveform. Now, in the mode 1, VAB is equal to plus ES, VBC minus ES by 2, VCA minus ES by 2. So, plot these value here. VAB plus VS, VBC minus VS by 2, and VCA minus VS by 2. So, with help of the values from the mode 2, mode 3, mode 4, mode 5, mode 6, with help of that draw the line voltage waveform. Now, expression for RMS value of line and phase voltage. Now, V phase is equal to 1 upon pi integration, limits of integration 0 to 2 pi by 3 ES upon 2 bracket square d omega t raised to half. Here, the maximum value of the phase voltage is the plus Vs by 2 or minus Vs by 2. The peak value is Es by 2. Therefore, V phase is equal to Es divided by root 6 or 0.41 into Es. The RMS value of line voltage is given by VL is equal to root 3 V phase. Therefore, VL is equal to 0.707 ES. Why there is no possibility of short circuit in the 120 degree conduction mode? Now, as we know, in the mode 1, T6, T1 are in conducting state. The range of mode 1 is 0 to 60 degree. Now, in between 60 to 120 degree, T1, T2 are in conducting state. In 120 to 180, T2, T3 are in conducting state. And in 180 to 240, T3, T4 are in conducting state. Means the power device from the same leg. Here T4 conducts after the 60 degree from the turn off of T1. Means in between 60 degree, definitely commutation of T1 takes place. So there is no possibility of short circuit. That's why in the 120 degree, there is no possibility of short circuit. Now, comparison between 180 degree and 120 degree. Now, in the 120 degree, at any instant of the time, 3 power devices are in conducting state. And in the 120 degree, 2 power devices are in conducting state. Now, in the 180 degree mode, there is no time gap between the turning off of one device and the turning on of the another device. If the commutation is failed, the DC source would experience a direct short circuit through the 2 SCR in the same leg. But in the 120 degree mode, there is 60 degree interval between turning off of one SCR and the turning on of other SCR in the same leg. So during this interval, definitely commutation takes place. So there is no possibility of short circuit. Now, in the 120 degree mode, since 3 SCRs conducts at any time, the potential of 2 terminal of the load can be defined at any time. However, in the 120 degree mode, since 2 SCRs conduct at any time, the potential of two terminals which are connected to the source through the outgoing SCRs can be defined between the potential of remaining 3 terminal remains undefined. Its potential depends upon the nature of the load. In the modes, the tripling harmonics are absent in the output voltages. These are the references.